Okay, so let's see. It says a non-uniform electric field given by E equals 3xi plus 4j pierces the Gauss cube as shown in figure. E is in N per coulomb and X is in meter. What is the electric flux through the right phase, the left phase, and the top phase? So as you can see here is the cube. And of course, there are totally 6 phases, facing left, right, front, back, and up, down. So it asks to calculate the E field, the electric flux through the Y phase. Let us consider this one first. This is the right phase. Okay, so here, the integration sign E dot dA, and then for the right phase, so we use R to represent right. Okay. So actually here we have E equals 3x I plus 4j like this. And for the right phase, we should know dA. We should know dA first. Actually, for this one, dA vector is dA. dA is the magnitude of this vector, and the direction. What is the direction of dA? It should be pointing to the positive x-axis. Positive x-axis. So it should be I hat pointing this side, dA. Okay, so we can consider E dot dA here, which will be integration of R, and then E. E is this one. We put it here, 3x I hat plus 4j. And then dotted with dA. dA is dA I hat. Okay, for the inner product in the Cartesian coordinate, we can have 9 identity. One is I dot I, I dot j, I dot k. Also, we could have j dot I, j dot j, j dot k. And also we can have k dot I, k dot j, k dot k. So actually we have 3 unit vector for the 2 operands. So there are totally 9 combinations. And actually it's easy to remember. I dot I will be 1, j dot j will be 1, k dot k will be 1. The unit vector dotted with itself will be 1. And for other combination, all of them are 0. Because the unit vector in the Cartesian coordinate are perpendicular to each other. So the inner product will be 0 between 2 of them. Okay, so here we can just distribute this one into here and here. So we have I dot I will be 1. So we have a 3x dA. 3x dA. And then here we have a j dot I. J dot I will be 0. So we just ignore this one. This 0. Okay, so here we have 3x dA here for this surface. For this surface, we have x to be 3 meters for this one. x equals 3. Okay, so here we should have x to be 3, x to be 3. And actually this area will be this side is 2, and this is a cube. So the area of this square will be 2 times 2, which is 4. The total area is 4 meters squared, because it's 2 times 2. And actually, this 3x is uniform over the surface. So it is like integrating a constant, which is nothing but 3 times 3 times 2 squared, which is this is the area. This is 3, this is x. So altogether, we have a 3 times 3 times 4, which is 36. 36 Newton meter square over Coulomb. Any questions? Okay, so we go to another one. So here we're supposed to find the plus for the left face, which is this one, the left face. So similarly, we can write E dot dA, take the integration for the left surface. Okay, so here we still have yes, we still have E equals 3x I dot I hat plus 4j hat. And here dA points to the left side rather than the right side, because dA should be pointing outside from the Gaussian surface. So here dA should be negative dA times I hat. This is the negative x-axis. Okay, so here we have a integration of L, and then 3xi hat plus 4j hat dotted with negative dA I hat. Okay, so similarly, we can distribute. So for the first term, we have a negative 3x dA integration of L. For the second term, similarly, we have a j dot I. J dot I will be 0. So in this case, we have negative 3, but here, this one, x is 1 meter. 1 meter for this surface. Okay. So here we should have x to be 1 meter. So we times 1 here, and actually still here we have area to be 4, 2 square. So finally we have a negative 12 Newton meter square per Coulomb. Okay, any questions? Okay, so we move to another one. We find the electric flux for the top phase. So the top phase is this one. So here, dA does not point to the x-axis anymore, along x-axis anymore. This one should be pointing to the positive y-axis. So we have a dA to be dA times j hat. Like this. Okay, so we can write integration of E dot dA over the top surface. So we can write 3x I hat plus 4j hat dotted with dA j hat. And then for the top surface, we can also distribute. For the first term, we have I dot j, which will be 0. So we have a 0 for this term. And for the second term, we have a j dot j will be 1. So we have a 4 for dA integrating over the top surface. So of course, this is the constant. So we have a 4 times 2 squared, which is a 16 nanometer square, Newton meter square per coulomb. Okay. So, any questions? Any questions? Okay. Okay, so actually we have not introduced Gauss law yet. Actually, we only introduced how to calculate the electric flux. And in such a way, we are introducing the Gauss law here. Okay, so it says for the Gauss law, it relates the net flux of an electric field through a closed surface, a Gaussian surface. So in this textbook, it usually says Gaussian surface, but actually it is actually the same as the closed surface. Okay, so to the net charge related to the net flux for a Gaussian surface to the net charge that is enclosed by the surface. It tells us that epsilon naught, which is a constant, the permittivity constant, 8.85 times 10 to minus 12. So this is phi, this is the net flux for a arbitrary Gaussian surface. And then this is the Q enclosed, ENC means enclosed by the surface. Okay, so we can also write it as this one. This looks easier, but actually this looks more complicated. But we usually use this one rather than the upper one. It is like for the Newton's second law of motion. In high school, you know F equals ma. So you may know two of them, and then you can use F equals ma to find the last one. And actually, for bachelor student, you may need to learn how to solve a differential equation. So usually, it should be in small letter. Usually in small letter. And actually, you know, acceleration is the derivative of the velocity and the second derivative of the displacement. So we usually write it as a m d d2x dt2, the second derivative of the displacement with respect to time. Okay, so as much as we have this one, we can write something like the differential equation. We are trying to solve the differential equation for more complicated tasks. In high school, if you only know F equals ma, usually you consider something called with an object with a constant acceleration, something like that. It's just like you try to throw a ball, and then you try to find the locus, how far it will go. But actually, for undergraduate study, we would like to solve more complicated things, just like here. It's just like F equals ma. These two numbers multiply together to be the third one. But actually, as we know, the definition of the flux will be the surface integral. So actually, we use the surface integral here, multiplied by the epsilon naught, equals the charge enclosed by the Gaussian surface. So here on the right side, we have four example to specify this. Yeah, as a demonstration. So as you can see here, we have two charges. This one is a positive charge. This one is a negative charge. So we have two charge in this region, and we can try to define the first Gaussian surface S1 to be this darker orange one, the darker one here. So this one actually enclose the positive charge. So actually, when you try to consider Q enclosed here, which is this positive charge, it doesn't relate it to this charge outside the Gaussian surface, because it means that enclosed means the charge is inside the Gaussian surface. So for S1, the Q enclosed is only this positive charge. And when you try to calculate the net flux for this Gaussian surface, you try to separate this Gaussian surface into many small parts. And then you try to calculate E dot dA one by one, and then you add them together using this integration. So that's the idea. And as much as this Q enclosed is positive, so you can simply imagine this term is also positive. This net flux for S1 should be positive. So here it says two charges equal in magnitude but opposite in sign. And the field lines that represent the net electric field for Gaussian surface are shown in the cross section. So the first one, phi1 means the net flux for S1 is positive. And then similarly for S2, this is the Gaussian surface enclosing only the negative charge. So you can simply imagine that this is negative, this is positive. So this one should be negative. So phi2 is negative for S2. And here we have a F3. S3 to be this one, which enclose nothing. Both the positive and negative charge are outside of this S3. So Q enclosed for S3 is 0. So epsilon naught is a positive value. So this one should be 0. So that the left side and right side equals each other. So you can simply imagine that the integration of E dot dA for this one is 0. Although part of it, this part is negative. For this part is storing. For this one is storing inside the Gaussian surface. So as this one, they are generally throwing outside, not necessarily 90 degrees to the surface, but at least it is throwing inside. So you can imagine these three contribute negative flux for S3. And for this one, they are throwing outside, so they are positive. They are positive value. So you can see maybe for this part we have a positive plus. For this part we have a negative plus, but they perfectly cancel each other according to the Gauss law, because we see that Q enclosed is 0. Q enclosed is 0. So the plus for this S3 must be 0. And for the last case, S4, which is the largest one, like an egg. So this one encloses both positive charge and negative charge. And so the Q enclosed for S4 should be this one added with this one. The charge is only a scalar, so you just add them together algebraically. So as I said, it is equal in magnitude but opposite in sign. So when you add them together, it's zero charge inside S4. So according to Gauss law, Q enclosed for S4 is also 0, and so phi 4 is also 0. So this is a simple demonstration for the Gauss law. Okay, any questions? Okay, so here shows how we can use the Gauss law for the most simplest case. It actually tells us that the Gauss law is compatible with the Coulomb's law, which we have learned in chapter 21. So it says S is a spherical Gaussian surface. A charge Q plus with a positive value is at the center of this spherical Gaussian surface. So if we try to apply the Gauss law for this Gaussian surface, Q enclosed is actually this Q, and we can imagine this E dot dA for this Gaussian surface. Actually, we have symmetrical property here because it is a spherical. All the distance from the center to the surface itself should be a constant, which is the radius of this sphere. The radius of this sphere. And for example, for this one, we have dA pointing outside and is perpendicular to the surface. So it should be in the radial distance, radial axis. You try to if you try to connect the center to that point, dA, which is perpendicular to this surface, should be on this axis. And we can also imagine that E is also in this direction, according to what we know before. So we know that this E dot dA, dA should have the same position, should have the same direction as the E. So E dot dA is nothing but E times A cosine 0 degree, which is 1. So we have an E dA here. So this is vector dot vector, and then it becomes a scalar. Okay, so far we got this one, and then due to symmetric, we know E should be uniform over the whole Gaussian surface because the distance between every point on the surface to the center should be the same. So we can simply imagine that this is a constant. So it can be fractal out. So we got epsilon naught E integration of a dA. Integration of dA is nothing but the surface area of this sphere. And I suppose in high school you should have learned the surface area for a sphere is 4 pi r squared. And I think in calculus class you also let this result using the rotational method to calculate the surface area. Just like if you have an axis and then you have a semicircle and then you try to rotate around the axis, then the surface area can be calculated in some sense. Okay, so this is the surface area of this sphere. Then we can just plug in this one here. So we got epsilon naught E 4 pi r squared equals Q enclosed, or we may simply write it as a Q. So finally, moving this term and these terms to the right side, we got E over 4 pi epsilon naught, 1 over 4 pi epsilon naught, which is actually K. And then we also have a Q enclosed, or Q here, over R squared. So which is actually the same as what we got using Coulomb's law. Coulomb's law, we know F equals K times Q1, Q2, and R squared. And according to the definition in chapter 22, we know E equals F over Q1 or Q0. Depends how you call the two charges. So according to these two, one is the Coulomb's law, one is the definition of the E field. We actually get the same result. So the Gauss law is compatible with what we have learned before. So I think this is simple. So let's take a look at a sample problem to see how we can use the Gauss law. So here it says in cross section a plastic spherical shell with a uniform charge Q to be negative 16 E and radius capital R to be 10 centimeter. A particle with charge Q equals 5 E is at the center. What is the electric field at point P1 at radial distance R1 to be 6 centimeters? This is P1, this is P1. This is a sphere. Actually, it is in 3D, but yeah, if we draw it in 3D, then you cannot see what is inside. So here, this figure only shows the cross section for the sphere and also the charge. The charge is at the center, and we would like to find the E field at point P. Okay. So here we try to define the Gaussian surface. Also, we will try to define this Gaussian surface to be a sphere and with a radius to be R1, like this. So you can see this one is actually maybe we can call this one S. This is S or S1. This is S1. And then we try to find the E field at this point P1. This is P1. Okay, so here, of course, we would like to use Gauss law for this S1. So we will have epsilon naught integration, the closed surface integration E dot dA equals Q enclosed A. Q enclosed for part A. So for this Gaussian surface, the only enclosed charge is small q. So this is small q. And similar to what we argue in the previous page, we know this one is epsilon naught E integration of dA. Because this is uniform. The charge distribute on the outer spherical should also be uniform. So the E field on this surface, Gaussian surface should also be uniform. So we can just have E dot dA to be EDA and then just factor out E outside. So we got this one equals Q. And then similarly, this one this one is nothing but 4 pi r square. So we have E to be 1 over 4 pi epsilon naught times Q is 5E. Q is 5E over R squared. And yeah, actually we can just define the radius of this Gaussian surface to be maybe R. And now we can just make R to be R1. Actually, any Gaussian surface with radius R to be less than this one, this one is capital R. If R is large, R is smaller or equal to capital R, or maybe strictly smaller. If R is strictly smaller than R, then yeah, this expression should be correct. But now we would like to find E at R1. Okay, so it will be like this. We can plug in the value. 1 over 4 pi epsilon naught is 8.99 times 10 to the 9th power times 5. E is 1.6 times 10 to minus 19 all over. This R is 6 centimeter, 0.06 quantity square. So this value is 2 times 10 to minus 6 Newton per coulomb, or you can write it as 2 micro Newton per coulomb. Okay, so this is the answer for the first case. Okay, any questions? Okay, so for the second one, we would like to find the E field at point P, which is outside the sphere cell. Yeah. So here we also define this Gaussian surface to be a sphere and with a larger radius. So here we may consider this is R, and R is larger than capital R. Okay, so here we can simply follow the same argument, but the only difference is we should have Q enclosed B. For Q enclosed B, we should add the small q with the capital Q. So here we should have E equals 1 over 4 pi epsilon naught times Q enclosed B over R squared. Here we should have R to be larger than capital R. So the only difference is that we change this Q enclosed A or Q to be Q enclosed B, and Q enclosed B is nothing but Q enclosed B is small q plus capital Q, because both small q and capital Q are inside this one is S2. So small q is still 5e, and then capital Q is a negative 16e. So altogether it is a negative 11e. So it is 1 over 4 pi epsilon naught and then negative 11e all over R squared. And here we would like to evaluate E for R equals R2. So we have 8.99 times 10 to the 9th power. And then here we have a negative 11 times 1.6 times 10 to minus 19 all over R2. R2 is 12 centimeter, 0.12 quantity squared. So it is negative 1.1 times 10 to minus 6 power Newton per coulomb, or you can write it as negative 1.1 micro Newton per Coulomb. Actually, if you would like to draw it out, the x-axis could be r, and then the y-axis is the E field, the magnitude of the E field, or maybe just the E field, in our axis. So it will be like something like this. So this is 5e k over r squared. 5ek over r squared, which means it is inversely proportional to r squared. Inversely proportional to r squared. And actually, this is 10 centimeter, which is capital R. And then here it suddenly jumps to negative 11 ek all over r squared. Something like this. Actually, this part still inversely proportional to r squared. Okay. Okay, so far, any questions? Okay, so we still have another sample problem. And actually here it asks you what is the net charge enclosed by the Gaussian cube of a sample problem 23.2. Actually, in this sample problem, we already find left, find right, and find top in the beginning of this hour. So here we also can see that for phi front and phi back, I think it should be phi back. Phi back should also be 0. It is obvious because for phi front is this one. And you can imagine this dA is pointing to the z-axis. Z-axis should be k hat. So you can simply imagine this one dotted with this one. I dot k is 0. J dot k is also 0. So you're integrating 0 is 0. And similarly for the back, dA is negative dA k hat. So you can also imagine this one is 0. So the remaining one is only bottom. We still need to find phi bottom. For phi bottom, which is this one. Phi bottom is this one. So actually dA is pointing to the negative y-axis, which is negative dA j hat. So here we have a integration for the bottom. Okay, so here we have 3xi hat plus 4j hat dotted with this negative dA j hat. Okay, so we can distribute. So for the first term, I dot j hat is 0. So this is 0. And the second one, 4j hat dotted with negative dA j hat. So we have a negative 4 dA. Integration of negative 4 dA. And then for the bottom. Okay, so here we have a negative 4 times 2 squared, which is negative 16 Newton meter square per Coulomb. this one is 5 photon. So the total flux or the net flux for this cube is actually summing all of them together, which is including this one on -12, 36, 16, 2 of the 0, and then also this -16. So it is nothing but a -12 plus 36 plus 16 minus 16. So the answer is 24 Newton meter square per Coulomb. This is the net flux for this Gaussian surface. So finally, Q enclosed of this Gaussian surface is phi over epsilon naught. If you still remember, phi is epsilon naught times Q enclosed. So Q enclosed is phi over epsilon naught. Okay, so this one is 24 over 8.85 times 10 to the minus 12. Sorry, should be the other way around. I make it the reverse way. So Q enclosed would be epsilon naught times phi. Make a mistake here. So it should be 8.85 times 10 to the minus 12 times 24. So the answer should be 2.1 times 10 to the negative 10 Coulomb. Or you can write it as a 210 picocoulomb. Actually, here we only know there are totally 210 picocoulomb charges inside this cube, but we are lacking of information how the charge distribute inside to really generate this flux. What we only know is the charge amount inside the box.